everyone. So it's late night here at India. So I am Shanmugan Nathan Raman, and thank you for being here. And today I'll be presenting our work titled Synthesizing Compositional Videos from Text Description. This is a joint work between the Computer Vision Imaging and Graphics Lab at IIT Gandhinagar and Adobe Research. The collaborators are Prajwal Singh, Kuldeep Kulkarni and Harsh Rangwani, the last two from Adobe. Over the next few minutes, I will walk you through a problem that has in many ways been hiding in plain sight in the text-to-video literature, the problem of compositionality. And then I will show you a simple training-free fix that we call Video-ASTAR. So that is the agenda for this talk. And let's go. So this is the typical text-to-video generation problem. So the text-to-video generation problem, it is called in short as T2V, is the task of producing a coherent video clip from a natural language description. So the pioneering example you see in this slide is Meta's Make a Video from 2022. The pipeline starts with a text prompt. In this case, a person doing yoga outdoor during a sunrise, passes it through a prayer, then a spatio-temporal decoder, frame interpolation, and finally super resolution stages to produce the output video. The key idea is that we learn what the world looks like from paired text image data, and we learn how the world moves from unsupervised video. So even back in 2022, the results were striking, and they kicked off an explosion of research. Since then, the field has converged on a dominant paradigm, latent video diffusion models. Instead of denoising in pixel space, we use a video encoder to compress frames into a compact latent representation, run the diffusion process there, and then decode back to pixel space, as it is evident from this slide. The denoising can be conditioned on text, images, or other signals, and a video-aware discriminator can be used during training of the autoencoder. This is the Align Your Latents paper from NVIDIA, which is shown in the slide, which really crystallized the recipe most modern T2V systems still use today. This is the abstract from Make a Video, text-to-video generation without text video data, the work I just mentioned. The intuition again is beautifully simple. Separate the what does the world look like question from how does the world move question. And you don't need paired text video data at all for making it work. Then came a Gen 1 from Runway, Yeser and colleagues, which introduced structure and content guided video synthesis. You can take an input video and edit it with a text prompt or a reference image while preserving structure. This pushed T2V into the realm of video editing, not just generation. Next came Magic Video. This is from ByteDance. This showed that you could do efficient T2V with the latent diffusion at 256 cross 256 with around 64 times fewer compute resources than pixel space methods. That made the technology far more practical. And more recently, Mavin from Zhang and colleagues tackled multi-action generation by splicing single action clips together using transition video infilling. We will come back to multi-action generation toward the end of this talk again, because it turns out that our method has interesting things to say there too. So in just a few years, the field has gone from can we even do this to a rich ecosystem of techniques. Let us now ask, why does any of this matter? Why do we care about text to video? Let me give you two concrete application areas. One is from the entertainment and storytelling. With a single sentence, Tom Cruise's face reflects focus, his eyes filled with purpose and drive. A model like Videocrafter 2 can produce a cinematic looking shot. This is huge for filmmakers, animators, advertisers, and game studios who can now prototype scenes that would otherwise require expensive shoots. The next example is from virtual tours and simulations. With camera control extensions like Camera CTRL, you can describe not just the scene, but the camera motion. A drone camera dolly zoom over a beautiful rocky river with a waterfall, and the model produces a fly-through. This unlocks real estate previews, virtual travel, training simulations, and more. So the demand is there. The question is whether the technology delivers. To answer that, we need to look. Let's start with some basics. So this is the structure of a latent video diffusion model. Here is the high-level architecture of this latent diffusion model. We have a video X0, right, which gets encoded into a latent vector Z0, and which passes through a decoder, and which reconstructs it back to X0 prime. The diffusion happens in the latent space. Let's just unpack this to get more meaning. So this is how a latent video diffusion model looks. The encoder takes input video frames, T frames at full spatial resolution, and produces a latent tensor of shape T, C, H by F, W by F, as shown in the figure, where F is the spatial downscaling factor. And the decoder reverses this. The whole autoencoder is trained end to end. Crucially, this gives us a much smaller tensor to do diffusion on, which is what makes modern T2V tractable. Now, here is where the magic happens. In the forward process, in the latent diffusion, we gradually add Gaussian noise to the clean latent over T steps, ending in pure noise drawn from standard normal. Each step follows a fixed Markov chain, as shown here. In the backward process, a neural network learns to reverse this. At each step, there is a prediction happening of the noise or the clean latent, and gradually the network denoises back to a usable signal. This is the standard diffusion recipe, just lifted to the video latent space. So this is a standard diffusion thing, latent diffusion applied to a video diffusion model. Okay. So let's move further. So when we zoom into the denoising network itself, what is that every step the reverse process looks like? It's a unit with three kinds of blocks: convolution layer, spatial transformers, and there is temporal transformer, as you can see from this figure. Right? The text prompt enters through cross-attention in the spatial transformer blocks. These are the pink blocks we have highlighted in red here. We will come back to these spatial transformer blocks because they are at the heart of the problem we identify and some of the loss functions we are going to define over them. Let's ask a question. Can model generate videos from text using T2V diffusion models? So with this whole machinery in place, the natural question is, can it actually do the job? Let's try a simple prompt, a banana and a keyboard. Here is what Videocrafter 2 produces. We see a banana, we see a laptop in the background, the temporal consistency is good, the visual quality is good. Let's see another example. The prompt is the burnt Shanghai, vibrant color. The model produces a vibrant Shanghai-like waterfront scene. Again, the model clearly has learned a lot. Next, the prompt goes a truck on the right side of a bicycle front view. We get a truck, we get a bicycle, frames are smooth. So at first glance, yes, the answer is a confident green check mark. The model can generate videos from text. So problem solved. Is it so? So if you look carefully, it doesn't seem so. Why is it? Now let's ask a different question. Not did it generate a video, but did it generate the right video? Look more carefully at these same three examples. In the first row, the prompt asked for a banana and a keyboard. We got bananas, multiple in fact, but the keyboard has been replaced by a laptop screen. The keyboard concept got absorbed. In the second row, the burnt Shanghai, the iconic Shanghai skyline is barely there. Instead, we see a strange amalgam that looks more like the Sydney Opera House with rainbow streaks. In the third row, a truck on the right side of a bicycle front view. We have a truck, but where is the bicycle? It is largely missing or merged with the truck in few frames. So the picture changes. This time, we get a red cross here because it's not generating the correct video, right? So the model fails to follow the prompt when the prompt is even mildly compositional. So this is the compositional video problem we are going to discuss. It drops objects, merges concepts, ignores spatial relationships. This is the compositional generational problem we are going to focus on this talk, which is based on our WHCV 2026 paper. How does the diffusion model know what to generate? To understand why this happens, we need to ask a more basic question, something like this, right? So the answer is quite simple. It is through cross-attention at the spatial layer. Let me unpack what that means. In a cross-attention layer like this, the noisy latent Z of t produces queries, and the text embeddings produce the keys k and the values v. Both are text generated. The attention scores are computed as softmax of q k transpose divided by square root of root d, like it is shown in the equation here. And these scores are used to mix the values of v. The key insight is this: the attention scores tell us for every spatial location in the image, how much each text token contributes to that location. The token dog might have high attention in the upper left region. Ball might have high attention in the lower right, for an example. That's how the model spatially grounds the language. Let's take this example. We can actually visualize the behavior we showed as equations through the diagram here. So here is a generation from the prompt. In a quiet park, an old man wearing a brown hat on the path with a side. Each panel shows the spatial attention map for a particular token at layer 5 of the spatial transformer in the architecture I just showed. You can see the dancing token light up when around the man's legs in the first image. Right? And bench lights up when the bench, where the bench is, sitting, where the man is sitting, rock, similarly localizes the rock. So the model does know where things should go. The grounding mechanism exists. So where does it go wrong? That is the question we want to ask. So what exactly the problem is? During diffusion steps, we can observe that the token attention gradually disappears, leading to missing objects. This is one of the problems, right? So as the thing progresses, you get the missing object. That is one of the problems. There are exactly three problems which are shown here. The first on the left is overlapping cross-attention maps. Different tokens end up attending to the same spatial regions, so concepts get fused into a single blob. The second in the middle is vanishing cross-attention. As we go from T63 to T0, so you can see that the attention region for a given token literally shrinks and fades away. By the end of denoising, the token has essentially zero spatial footprint and the corresponding object is dropped from the generation. So that is the second problem in the middle. And the third problem is something like the object should be packed together. That I will come to it after some time. So the problem is real. We are losing information in the attention maps. The next question is, how do we fix it? This is the solution we propose in this paper. So our fix is training free. We don't retrain this video crafter 2 model, which is shown here, which has already pre-trained, or any other backbone can replace this also. Instead, at inference time, between denoising steps, we apply a small optimization on the latent ZT. The framework is shown here. At each denoising step, we extract the cross-attention maps for the tokens of interest, K tokens here, compute 3 losses on those attention maps, take a gradient with respect to ZT, and update the ZD star to be ZD minus the gradient of the loss function, alpha times gradient of the loss function. Then we sample ZT minus 1 from the updated ZT and keep iterating it over during the inference time. This is a test time intervention, and it composes cleanly with Video crafter 2 or any similar backbone. The core question is, what should those 3 losses be? Let's go one by one. The first loss tackles the overlapping attention maps problem. We call it the segregation loss, LSEG. The idea is to penalize spatial overlap between 2 attention maps that correspond to different concept tokens. Mathematically, for every pair of concept tokens, M and N, we compute something like an intersection over union, which is in the numerator here of their attention maps. And equation 3 in this slide mentions the same. The numerator is the element-wise minimum of the 2 attention maps summed over all spatial locations. And the denominator is their sum, which is like a union. So when the maps overlap heavily, this ratio is high. When they are disjoint, it is near 0. So through that, we can easily have it as a loss function, which is this LSEG, right? So here is a cartoon to make this concrete. We have a prompt with 2 concepts, dog and cat. The attention map, AM, corresponds to dog, shown in blue, and AN corresponds to cat, shown in orange. As you can see, they are splitting into each other in the middle region. So how do we fix the problem? With the numerator here. Right? The numerator of our loss measures exactly this overlap region, the element-wise minimum of AM and AN. Right. So when the attention maps overlap heavily, in this, like in this picture, the loss reads high. So the gradient pushes the latent in a direction that separates the maps, something like this. Right. After optimization, the maps for dog and cat cleanly separate over their respective silhouettes. The loss is now low, and as a downstream consequence, the generated image has both a distinct dog and a distinct cat. Concept fusion is solved. This is the first problem solved. The next problem, how can we fix the second problem, which is the retention, the slow disappearance of some of the concepts or objects, right? The second loss tackles the vanishing attention problem. We call it the attention retention loss, LRET. The intuition is at every denoising step, we want the cross-attention map to retain the spatial regions it had at earlier steps. So we compute a kind of retention IOU, intersection over union, between the current attention map and a reference mask and minimize the deviation. Right? So as shown in this equation. So let's take an example, right? So where is the reference mask? Let's start at diffusion step 1 here. The attention map ATM for token M looks like this. There is a clear high attention region on the dog. We threshold this attention map to produce a binary map MTM. At step T, this mask captures where the token wanted to attend to at this point in time. Now we move to step T-1, the next denoising step. At step T-1, the attention map A T-1M has shifted, perhaps weakened, perhaps moved. Now we compare the new attention map A T-1M against the mask MTM we generated at the previous step. This is the comparison highlighted in the loss formula's numerator. Right? The denominator normalizes by the union. if the new attention still covers the masked region well, the IOU is high and the loss term is low, good, no correction needed. But if the attention has shrunk or drifted away from the masked region, the IOU will be low, and the loss will be high. The gradient pushes the latent so that the text attention map is forced back into the right. Next attention map is forced back into the right region. This is what stops the attention from vanishing across the denoising steps. So aggregation and retention together fix the single frame compositionality. But video has another axis time, and there is a third failure mode which we want to discuss. Right? The third loss tackles the case where attention for different tokens drift spatially across frames. If cat attends to the right, bench attends to the left of the frame later, they shouldn't drift away, leading to temporal inconsistency. We define the centroid loss L-cent, defined like this. For every frame T and every concept token, we compute the spatial centroid of the attention map. The centroid has a row coordinate and a column coordinate given by equations 5 and 6 shown here. And these are essentially weighted averages of pixel positions weighted by the attention values. We stack them into per frame centroid in equation 7, and the loss in equation 8 is just the L2 distance between the centroids of the token pairs. The diagram on the bottom left shows the inclusion. The per frame attention maps have centroids that are flying apart. The centroid loss pulls them back together. So let's see a pictorial representation to understand this. Here is a scene with a bench, a rock, and a cat. Initially, the attention maps for these objects sit at slightly different spatial locations across frames. How can we fix this problem? By this centroid loss. So the row centroid, equation 5, gives us the vertical center of mass of each attention map. Visually, these are the horizontal lines passing through the each object's attention. And the column centroid in equation 6 gives us the horizontal center of mass. These are the vertical lines through the object's attention. And stacking row and column centroids give us the per frame 2D centroid of each object, which is the equation 7 we mentioned on the left-hand side, and one XY coordinate per concept per frame. And the centroid loss in equation 8 simply enforces that these centroids stay consistent across the frames. After optimization, the bench, rock, and cat each maintain a stable centroid through time, so they don't jitter or teleport. That's the idea. So overall, we get this thing. This is the full picture. Our framework, which we call Video-ASTAR, combines all three losses. Attention segregation fixes overlapping maps. Centroid loss keeps attention spatially stable across frames. Attention retention keeps attention from vanishing across denoising steps. These three gradients are added and used to update the latent at each diffusion step. No retraining, no extra data, just smarter optimization step, that is single step update each time. The name Video-ASTAR stands for attention, segregation, temporal centroid, and attention retention applied to videos. That's why we call it Video-ASTAR. So how well does the proposed method work? Let's see how it actually delivers. So this is a old man and tiger example. There are two prompts side by side. The left is in a quiet forest, an old man wearing a brown hat sitting on the bench beside a rock stone on the path, 4K high resolution. The right is the same scene with a tiger instead of a man. Right? The top row is the baseline, which is the Video Crafter 2, and the bottom is our Video Crafter 2 plus our Video-ASTAR optimizer around it. So in the bottom row, especially, you can notice that the man, the bench, the rock, all composited correctly. Same on the right with the tiger. So we got perfect results compared to the first and the second. If you see the first one, there is no bench, and there are a lot of missing concepts and other problems we are facing. Let's see another example. A tennis racket and a bottle. The first row is the baseline, and the last is our uh, uh, A-star plus video crafter. As you can clearly see, the last row shows both a tennis racket and a bottle in every frame with a consistent code setting. So qualitatively, the method does what it is designed to do. Let me show some quantitative results. So we evaluate on the standard T2V compositionality benchmarks. The columns are spatial relationship. The higher, the better. Multiple objects, higher is better. And overall consistency, higher is better. Temporal consistency, which is also for which the lower is better. So this one, if you see the Video-ASTAR, which is in the bottom, achieves quite good in most of the benchmarks, as you can see from the slide. So you can refer to the paper for more details in the interest of time. Okay. So the effect of mask in attention retention loss and loss ablation. So now let's do two ablation studies to this thing. So the two ablation studies. In the interest of time, I will leave it for you to work with the paper to understand it better. And let me move further. Yeah. So here are some of the nice results generated by our thing. So directly, I will jump to the other one, which I asked a question earlier, right? So the multi-action video generation. So the work extends very well to the multi-action video generation. So far, every prompt has a single action, sitting, walking, or standing. What if the prompt has two actions in sequence, like an old man walking on the path, then sitting on the path? This is the multi-action setting we want to uh, discuss as shown in this slide. So there is a FIFO baseline, which is shown here, which is given here. So there are some problems with this. So in the first, the man walks the whole time and never sits, right? In the FIFO baseline. And the second, the tiger transitions, but its consistency across frames is disrupted. In the third, the man box, we never see a clear transition to a seated position. So FIFO alone struggles to enact a true multi-action sequence. But we propose two strategies, token swap and latent interpolation. So you can look at our paper to understand better. So we are able to achieve much more smoother transitions and also all the actions are followed in the sequence. So it's a multi-action thing. So this, in the interest of time, I will leave it for discussion. So this brings me to the end. So to summarize, the text-to-video models look impressive on single prompts, but break on compositional ones. They drop objects, fuse concepts, and let us attention drift. We diagnose this as three concrete failures in the cross-attention dynamics: overlapping maps, vanishing attention over denoising, and centroid drift over frames. We propose three corresponding training-free losses: segregation, retention, and centroid. Applied at inference time on the noisy latent, the combination Video-ASTAR plugs into this pre-trained video crafter 2 without any retraining and produces measurable gains across every compositionality benchmark we tested, plus an extension to multi-action generation, as I showed earlier, with two techniques, token swapping and latent interpolation. And I would now love to take your questions and hear your thoughts. Thank you very much.